Oh, she sits there, yes.
And everyone, I put the solutions in Canvas. It's at the end of module 3 though. So go all the way into module 3, you'll see the solutions. There's a blank copy there too if you want a blank copy. Hey, today, this is the fun part at the end of the course, the last module, we just go backwards. We do antiderivatives. Now, it starts in 4.9. So today we start in 4.9 and we'll get up into 5.1. Where we build off this concept of antiderivative. It means just go from velocity back to position. Go from acceleration back to velocity. And so we just need a reverse power rule. That's what we need. We need a reverse power rule, like something like this. X cubed would go to 3x squared. We need to somehow come up with an expression of how you go from 3x squared up to x cubed for this antiderivative process. You could probably figure it out on your own. This power has to get added by how much?
1.
1. So that's part of it. So the rule will be, all right, let's add 1.
Don't you have to account for a constant too?
Good call. There you go. We have to account for any constant that might pop up. And when he's pointing out like the x cubed plus like 5 or something. And the derivative of a constant is always what? 0. So we'll have to figure out like what to write every time because there could be a constant there or something.
Did you multiply by the reciprocal to get rid of the 3?
And that's what we'll do. That's the rule. So the rule is, I guess we'll just say, take this expression you got, add 1 to the top, and then divide by that number. Just like that. That'll be the antiderivative expression. And then Ben says, but wait, there could be a constant in the original thing, so every time just put a plus C on it. A plus constant. Just every time put a plus C. Well, let's try one. 3x squared. Pretend that was the derivative of some function. Can you figure this out?
Yeah, so x cubed.
And hey everyone, I'm writing it this way. I won't write it like this forever. But it's the idea of, oh, we're going backwards, so I'm kind of writing it backwards. We got to go from 3x squared and back to the original f of x. So the rule is, just add 1 to that power. What about this constant here? Just include it. Remember the constant rules? We just keep constants in front?
Mm-hmm.
Cool. So x squared would become x to the
3rd.
3rd?
Mm-hmm.
But then now you got to divide by the number you just wrote. Maybe I should put that in yellow. This is the first time we're doing that. I'll get that out of the way. We added 1 to that, right? But the rule says also you got to divide by that. Whatever that power was right there, you also got to divide by it. So x cubed over a what? 3. And then I'll always write plus constant. Ben says there could be a constant there, so we'll take care of that, no problem. How about every time we write plus C? Unless you want to write plus K. It's C for constant, right? Or think of a person's name like Charlie. Plus Charlie. Every time, just plus Charlie. And what happened to these trees? They cancel. So is that right? That one is the derivative x cubed 3x squared? Does that make sense?
Mm-hmm.
So we're doing antiderivatives. This is 4.9. We'll spend a lot of time in here. Make sure you're You're pretty good with all of them. What about trig functions? Well, no problem here, we'll just go that way now, right?
Mhm.
What's the antiderivative of cosine of x?
Sine.
Sine of x. What's the antiderivative of sine of x? Negative cosine of x. What's the antiderivative of negative cosine of x? Negative sine of x. But we should put those other trig functions down. What was the derivative of tangent of x?
Secant square x.
So how about, I'll just write this below it. And I'll just put an arrow like this indicating differentiate. I'll put an arrow like this to mean antiderivative. So the antiderivative of secant squared of x is
Tangent.
tangent of x, and then I'll plus c, right, Ben? I'd have to put a plus c. We don't have to write that over here. We'll know, always put plus c. There could have been a constant there, because the derivative of the constant would be 0, we wouldn't see it. We'll just plus c everything. Do you remember secant's derivative?
Secant x tan x.
Secant x, tan x. All right, I'll put an arrow for differentiate. So we're good, there's the trigs. Wait, aren't there two other trig functions? Yeah, they don't come as often. If you want to put them down, you can. You just put an arrow up, go up that way. If you recall, like, I can speak about them. Cotangent x, the derivative is negative cosecant squared. So negative cosecant squared to cotangent x would do the same. Want me to write those?
No.
I'll put them down since we haven't seen them in a while. Have you noticed they don't come up often? I know. You're like, you rarely see them. I'll put them down. Cotangent x, its derivative was negative cosecant squared x. Well, then the antiderivative of a negative cosecant squared would be a positive cotangent x. And then the other one was cosecant x, which was negative cosecant x, cotangent x. And then, just see, I'll pick problems in the textbook, see how often these come up. Not too often. All right, let's try one. How about, the first few times I'm gonna write it this way, because I'm trying to emphasize it. We're just going in reverse now. Like this is velocity, this would be position, right?
Mhm.
Well, if this was acceleration, this would be velocity. So how about x to the fifth minus 4x to the third plus 2x squared. Yeah, I'll leave 2x squared plus 5x plus 7. All right, we gotta do all 1, 2, 3, 4. We gotta do all 5 of these, and we're gonna find the antiderivative. This is called a polynomial. Well, each one of these are these monomials. We'll do each monomial separately. What would x to the fifth become?
X to 6.
Good job. Look, he pumps it up by 1. He pumps the power up by 1, and then he just divides by that number. That's what this rule means, right here. Pump up that power by 1, then divide by it. All right, then there's a minus. Cool.
Mhm.
Good, Jess?
So you only have to do the plus C at the end, right?
That's right. You don't have to put 6
For
plus
each
C's.
one. Okay.
But because think about it, I want to point this out. You wouldn't be wrong if you put 6 different variables down, but 6 unknown constants that we don't know is just one unknown constant. There you go.
Okay.
I'd be like, I can't mark Jess wrong. She put plus C plus D plus E plus F plus G. She's saying these are some unknown constants, but they could sum to 1 plus C. All right, that 4 stays. What's that become?
X to the power 4 divided by 4.
Now, do you want to do something? Make it look pretty?
Yeah.
Yeah, let's do it. Alright, the 2 stays x squared.
3. 3.
X, you pump it up by 1, x cubed, then you divide by that number. Hey, how could you check these?
Take the derivative.
Yeah, I want just every time you like, I don't know if I did it right, just differentiate it real quick, you should pop right back to where you were. Take the derivative. Okay, 5, x to the
2.
over.
2.
Alright, be careful of this.
7x.
I don't know why, you got it. Some people put 0, because we're so used to derivative of constant 0, so they're thinking derivative, but the antiderivative of 7, you're saying is just 7 with the letter
X.
x to a 1 over 1. Well, 7 is. And now finally, I'll put down the plus c. Plus constant. There it is. Now, somebody got it? Oh, what's that?
Would 7x be over half something?
Yeah, but you don't have to write it. You know why?
Oh, it's fine.
Good deal. And you figure it, you're like, oh, it's 1. It'd be over 1. You're like, I don't have to write that. Just remember, constants turn into that number of the x. And maybe there's a constant here, because the derivative, like, maybe there was a 17. We're trying to figure out what it was. The original thing. Maybe there was a 17 here, and the derivative of 17 was 0. That's why we just write that every time. Antiderivatives. Alright. So if we know all the tricks, we got every type of like polynomial down. Let's look at the strange cases. You go, what are you talking about? Like square root of x. So let's look at that. You know, sometimes things are to the 1/2 power. Well, let's start slow and then build off that. By the way, you don't have to write it like this in your notes. Section 4.9, every time I teach calc, I'll spend at least the first portion of class going up this way, just to emphasize, oh, we're going in reverse, right? But in your notes, you might write this underneath this. That's nothing wrong with that. We gotta make that a power, x to the what?
Half.
Alright, now you gotta pump that 1/2 up by 1. I don't know how great you are with fractions.
3x.
Good job. I mean, seriously. If not, you'll probably get used to it. If you're ever like, I can't stand fractions, you pull out that calculator, what's 1/2 plus 1, you know, and fract the thing. But yeah, 1/2 plus 1, you got it, 3/2. So I'm going to get x to a 3/2. Now I have to divide 3/2. Now that looks kind of sloppy, doesn't it? So when I think about this in math, you'll get used to this as well, because you'll do it like 100 times. No lie, 100 times. In math, if you divide 3/2, that's the same thing as multiplying
2/3.
2/3. So I'm just going to take my chalk here and just flip it, right? 2 here, 3 here. Did anyone say that? It means the same thing. It looks better. That was really a complex fraction the way I was leaving it. We shouldn't leave complex fractions. So we shouldn't write it as x to the 3/2 over 3/2 or over a 1.5. We should write, flip it, 2/3. Oh, and don't forget my plus what?
C.
Plus c. Will the plus c ever become really important? Yeah, a couple problems. And they call them initial value problems. Initial value problem will be a problem where they give you an initial value and it gives you enough information to find c. So I'd like to give you an example of that. So and every time we're just going to put plus c, right? But what if there's an initial value problem? You go, what does that mean? It means they've given you one initial value from the function. All right. Right? Stay right there. This is given. This was given to you in the problem. And the question is, find the antiderivative of this expression. So we're going to go find f of x again. I'm going to write down exactly what we had. But this is going to allow me to figure out the constant. Okay? That's what it's going to do. So they call it an initial value problem, or they call it that. Who's going to take differential equations eventually? That's what they, IVP. You'll see this little IVP, initial value problem. See calc did. So all right, they just means they gave me some initial value from this function. Well, I'll do it again. Here's f of x. X to the 3/2 divide 3/2. Wait a minute. that looks weird, I say multiply what?
2/3 plus C.
2/3, so it looks better. Right? And then I never forget to write what?
C.
Plus C. Now we wrote that, we're gonna dive in here, substitute things, and we're gonna figure out the constant. Okay. So I can erase this part here, get this out of the way, so we have room. I'm done except for one thing. All this is right, I wanna figure that number out. This allows me to find C. So, when they write this like this in math, you know in pre-calc, this is the letter X, this is the letter Y. So that's X, that's f of X. That's X, that's f of X. That's X, that's Y. So put in X right there. 4. We have equals, there's 3, put the 3 where? Here. And then you get 2/3 of 4 to 3 halves equals 3. Now run if you're like, I don't know how to do 4 to 3 halves. I know the calculator does it, but you don't need a calculator. It means the square root of 4 cubed. That's what that expression means. It means the square root of 4 raised to the third power. Now I know you can do that in your head.
8.
But square root of 4 is 2.
8.
So when they do those, they do numbers you could do in your head. But if you have to, pull out the tool, figure out what that is. We're gonna get this C eventually. Right? That's 3. 2/3, Art, thank you, you said this is 8. When you multiply fractions, just glue across, right? 2 times 8 is 8/3.
So 9/16, right?
Yeah, because if I'm going to take that 3, you're right. If I have to subtract 16/3, everyone, to get C. 3 minus 16/3 equals C, right? I subtract 16/3 from both sides. Then I need a common denominator. Well, that's 9/3. What's 9/3 minus 16/3? -7/3? Is that
Yeah.
right?
Yep.
9/3, subtract 16/3. Again, if you're like, oh, I hate fractions, you could go, let me see this real quick. So I'm getting 9/3 minus 16/3,
-7/3.
-7/3. Hey, sometimes students, you did all this work, you got C and they leave the answer like this, but I'll go back to the question, go, what were you asking for? I wanted you to find the original function of X with the initial value. What it means, I can rewrite all this, but I can now fill in C. C is what? So here's my answer. My solution to the initial value problem, f of X, the function, is 2/3 X to the 3 halves minus a 7/3. I found C this time. But you can only find C if they give you an initial value, right? They don't give you an initial value, plus C, plus C, plus C, plus C. Like minus C.
In definite integral, you don't need the C, right?
That's right.
Okay.
And when eventually we'll get into something called integrals. These things called indefinite integrals, which just deals with are good. Super job. Hey, what else is weird? Alright. There's one strange one. Only one though. Because that wasn't that bad, right? Don't you agree? Antiderivative, this is all we do, right? F prime of X was n, X to the n. I guess f of X just equals this, huh? Don't agree?
Mm-hmm.
Works with any alignment well. First I should put an easy one. What about the special cases? What are you talking about? The functions that aren't polynomials or monomials, some are exponential. Well, I bet you get it.
They
Same.
the same.
What was the derivative of the x? EDX. What's the antiderivative of the x?
We just add plus C.
Just put plus c. Gotta love EDX, right? But who's EDX's inverse? Natural log x. I'm gonna have to put that over here. A lot of you know it's derivative. Alright, what was the derivative of that?
1 over x.
Okay. So that means I'll get the y prime equals out of the way. I think I'll down there or up there, huh? Like I've been doing here. Alright, so I know, be careful.
That's x to the power minus 1, right?
So you're on your test, right?
Uh-huh.
Not that you're like, that's x to the negative 1 power, right?
Mhm.
And you're like, well, I know the rule. Just add 1 and what? Divide by it. And you'd see it. You're like, okay, here I go. X to the, if you add 1 to a negative 1, you get 0. And then you'd be like,
Oh,
wait a minute, you can't do that. You can't what? Divide by 0 in math? That's what, undefined?
Mhm.
That's not the solution.
Isn't
So this
that
is that one special case.
So there'd be no.
What is it?
You're not
natural log
dividing.
of x?
You're right, but that, so this would, when this would happen, if you accidentally did it, Amber, you'd be like, wait a minute. This is my special case. I know the antiderivative of 1 over x becomes this what? Natural log of x. So you go, for this one case, for x to a negative 1 or 1 over x, it just becomes a what? Natural log of x. And then I put plus 1.
see.
So just make a note about that. Go, all right, I'm ready for that. The 1 over x, right? 1 over x, 1 over, but everyone be careful. It doesn't happen with 1 over x squared. It doesn't happen with 1 over x cubed. It doesn't happen with 1 over x to the 4th. It only happens with 1 over what? 1 over x. Cool?
So are you just gonna give us the just f of x equals natural log?
That's right.
Or are you just gonna give us the derivative?
Yeah, the derivative, and then you'll find it.
On the test, is it possible we can just do the integral symbol for it?
Yeah, that's what's coming up. I love this. He's got knowledge of calculus. So in 4.9, everyone, and they haven't shown this little symbol yet, this integral symbol which is coming up, it appears in 5.1. Start writing it like that if you're used to it. Now when this is the symbol they write, they go like this. We'll talk more about what this thing means. Right? Now they do put a dx off to the side here. This means with respect to x, this dx here, don't let it bother you. You go, what the heck is that? But we're saying this is equal to the same answer, what was it?
Natural log of x.
Natural log of x plus a constant.
Constant.
Put this in your notes to everyone. When you do go backwards on this, the real definition is this. We have to put absolute value bars in this. So why do we have to do that? Because, do you all know about the actual Latin logarithmic function? It's off to the right, so you can't put negative values in it. Like on your calculator, if you took the natural log of -2, it's undefined. If you took the natural log of it, it's undefined. So, if you're going backwards, then you're saying, well, I'm assuming this x was already some unknown variable, then we're going to always have to put what here?
Absolute value.
Does that make sense? I know we didn't do that when we differentiated, but I'm going to put that now. When you go this way, Amber, put this down. That when you do the integral that we're talking about, this antiderivative, we're going to put bars around the x. Because x could have been some negative number originally. And we're like, well, natural log of negative numbers don't exist in the real number system. Absolute value bar every time.
So, professor, so antiderivative of 1 over x is natural log absolute value of x. What about the natural log of x? That's also absolute value of natural log of x, antiderivative?
That's right.
Okay.
That's it. That's exactly it. Very good. And when you see why we're doing this, give you that, I know it kind of throw you go, why am I going to do that every time? You'll probably, anybody use Wolfram Alpha for support? Sometimes they don't write it there. I noticed that. They'll just put ln, they'll put parentheses, but we really should put that in case someone put into this expression a negative value. Cool? Alright, so I think we've covered every special case, huh? But, see this symbol, everyone? It represents integral. I haven't shown it yet. Some people are familiar with it because they don't introduce this till section what? 5.1. But what we're saying is, if you want to start writing it, you could say, alright, well then the integral of x squared, yeah, you can just ignore this dx for now. We'll talk more about that. It just means you're using the variable x here. See, if they had other in calculus 2, you get into like dy's and dt's and stuff. That means you got to integrate it with respect to that letter. Well, if I integrate this with respect to x squared, that means I'm finding the antiderivative of this. I'll put an equal sign. Go ahead, Amber, pump it up by 1, x to the what? Third, divide the
3.
3, and then I put a plus what?
C.
So whatever your, okay, yeah,
So if you want to get used to that symbol, if you want to start using it, Raj was like, I'm going to write it like this in my notes because I'm going to get used to that. This is how you can write antiderivatives. It's called an integral. Now there's some meaning to this because it has some application. It deals with area under curves and stuff like that. That's what I want to build. I want to make sure you understand that. So it's an elongated S though. Doesn't it look like an elongated S? Like an elongated S, like you're summing something. Something's getting infinitely summed. There's a summation of an infinite amount of values and stuff. Infinite amount of like rectangles, if you will, and you'll see it when we build on that today. But if you just wanted to start writing that now, all right, since you mentioned it, I was like, yeah, let's show it to the class. It's like a stretched out elongated S, right? What's on the cover? Anyone see it? There it is. Kaboom. I know, there it is. The integral symbol. It's like an elongated antiderivative. Antiderivative. Now eventually we'll put some numbers on here today. And that'll mean something. You get to plug them in. Cool. I think we've covered all the what? The crazy ones, but and when this happens 100 times in Calc 1 and Calc 2, be careful. No. People do it all the time. That's not right. Hey, can I erase this?
Mhm.
We got it. Pump it up by 1, divide by that number.
so
That's not
it's
it.
X to the,
That ln of x, that natural log of x is only for a what? 1 over a simple what?
X.
X, that's it. So this, you're back to that rule. So let me get this out of the way. You're back applying that rule. So think about this. This is like us saying this. Y'all write it again like this. You're like, all right, there's some derivative of x. It's 1 over x squared. Who can write that so it's up in the numerator?
Negative
X
2.
to the negative 2.
You got it? Everyone agree? X to a negative 2?
Mhm.
Alright, now, be careful. You gotta pump that up by 1 integer and then divide by that new number.
Yep.
So
What's negative 2 add 1?
Negative 1.
Yeah, you're like negative 2 on a number line, add 1, you're like, you didn't go to negative 3. Negative 2 plus 1 gives you a
negative 1.
negative 1. So I'm gonna write this. X to a negative 1. Now you gotta divide by this number, which is a,
Negative.
and then I have to put plus what?
C.
C.
Can we do negative 1 over X?
That looks way better than that. Please do it. Cal, please write it like that. Don't leave it like that. Let's never leave negative exponents. It's like, rewrite this. That means 1 over x, right?
Mhm.
And it's negative. So she's saying just write negative and then put the x down here. You could put that minus like right in the middle. See the negative that appeared? Just put it off to the side. You got a 1 over x and then plus. That's way better because eventually they're going to be like this. Amber, plug in x equals 3. And you're like, okay, you're 3. Looks weird when you plug it like that. You know? So here, let me write it like this. Then this means, now I do that on my test, and I want to check. I want to check my answer.
Take the derivative.
Take the derivatives. You should come back to that. You can check all these. Every one of them. But some will get into, you go, when does that chain rule popping up? I'll tell you, not until section 5.5. We're in 4.9, right? So we'll spend the bulk of the time on that. It's way down at the end. 5.5 is called the substitution rule, and it's the reverse of the chain rule. It's fun though, you'll like it. You go, what do I do? And you'll do it every time. Cool. Alright, We'll do some more in 49. I'm looking for a weird one. So I'm scanning page 349. If anybody's got page 349 open, feel free to scan for a goofy one. I will too. If I tell you it's not worth it, we're not going to deal with it now, that's okay. Again, I think the strangest one I saw is number 34. This is the weirdest one I saw.
Or 44.
If you see one, let me know. I'll tell you like, oh, that's good or that stinks.
41 also.
I saw this one. First of all, they used T. And they had that. Now what do they want you to get? F of T. Now, they wrote this off to the side, everyone. So what kind of problem is this? Initial value.
Theorem.
Well, I like that theorem. No, it was an initial value problem, but
Oh, yeah.
hey, how about this, Amber? The initial value theorem is if they give you an initial value value, you got to plug it in and figure out C, right? I also, when I want to do, before we jump to the next section, let's definitely do ones like 59 and 61 and 63. They got the trig functions. We haven't done any of those yet, right? They're easy though, just SES, go that way. But I should put something else down. Charlie Sheen, Charlie Sheen, Charlie Sheen, Charlie Sheen. This is pi over 2, right? That's pi. That's 3 pi over 2.
Mm-hmm.
This is the point 0, 1. This is the point.
Negative 1, 0.
This is the point
0,
1, 0, and I note down here a 0 and a what?
Negative 1.
Because when we get a plug, if we're going to have to do initial value problems, everyone, they always like to do things at 0. They want to make it easy for you to figure out values. So get used to that. We're thinking about, you're going to find the sine of 0, and the cosine of 0, and the sine of 0, and the cosine of 0. You're going to get used to like just knowing these, so you don't have to keep going back to the calculator to figure out what the heck's cosine of 0. You get tired of it. You just go, I know cosine of 0 is 1, sine of 0 is 0. All right. I'm going to continue to write this way. Remember, just for emphasis, antiderivative. All right, what's t become?
T squared over 2.
Good job. Sometimes I see that on a test. What's the error? Right. Now it depends. What if a student did every problem perfectly right, and they did this once? Oh, LOL, right? You're like, they meant this is what, it's just something I do. Something I might do on the board. But if a student did on every problem, you're like, then you're concerned. Does that make sense? It sometimes will happen. You'll go, oh, for crying out loud. You'll laugh. You'll go, I did derivative. I meant to do what? Antiderivative. So this becomes t squared over
2.
2. Now here's that t to the negative 3. What's negative 3 add 1?
Negative 2.
And then plus but look, I have to, look at this. What does this mean? I gotta find the what? Let's find C. Now, what's another way to write this?
So f of 1 equals to 1 square over 2
Minus
minus.
1 in top,
Mm-hmm.
2 stays down here.
2 squared. T squared.
Don't I go that? All right. And where's this going?
2.
That's gonna be t, and then 6 is over to the left, right?
Mm-hmm.
All right. 6 is, oh good, I love ones. 1 squared. My favorite is 0, because everyone, what's 0 squared? 0 plus 2, zeros are great. Like here we go, and 1 squared, sorry, that's 1. Oh good,
Oh, that's
easy math, let's see.
6.
See, 6. It wasn't like the last one that I made up with the fractions, good. See, is 6. Now, final answer?
No,
I
5.
got it easier when I can just go back here, erase plus C and put plus 6.
Yep. Mm-hmm.
I should use this one. This one looks best. Alright, let's do some trig.
What
Don't
about-
worry, Owen, you're gonna get much, do you know how much more practice you're gonna get on this? Section 5.2, section 5.3, section 5.4, over and over and over, you will be doing this. So you're gonna get a lot, I didn't want you to think like this is one section, we move on. You just build on this, that's all we're doing in chapter 5. We're finding antiderivatives. But we see all the application, and what it means. What's it mean to go from velocity back to position, right? What's it represent graphically? We put in numbers, what do the numbers mean? We'll talk about that. Cool? And work on that one?
Yeah.
That would be the final answer, right? I was able to put the C in. If they didn't give me this, I just would have written plus C, right?
Yeah.
Professor, what about number 41? Did they do like double derivative, number 41?
Let me look at that one. Oh yeah, let's do it. And when they give you second derivative, you get to go all the way back to the original. Now when I keep writing backwards, I promise you I won't do this all the time. When you're writing this in your notes, feel free to flow like you do right always, top to bottom in the notebook. But I'll do it, this is probably one of the last times I'll do this to go, hey, you're going this way, so I gotta go really low here now. F double prime,
Theta.
did they use theta?
Yes, sir.
Alright, what do they got now?
Sine theta plus cosine theta. And f of 0 equals to 3.
Up. So here we go. It's an IDP again. They gave you a couple numbers. What did they give us?
F of 0 equals to 3.
Okay.
And f prime of 0 equals to 4.
Alright. Two initial values, huh? Alright, can you get to f prime?
Yeah. So negative cosine theta.
Oh, I love it. Look, you're going this way.
Minus sign theta.
No,
Minus, we're going from a positive sign to a negative what?
cosine
Negative cos. So you're negative cosine.
plus sine theta.
Negative sign theta.
And a positive cos goes to a
Positive sign.
do great. And when we're going this way, aren't we? For antiderivative. Does that make sense? Before we differentiated, no, we're just going that way. Negatives on the third and the fourth.
And then include.
So you're saying plus sign, huh?
Plus c.
You're like, should we go that? Well, let's stop for a second and figure out C, huh?
Anything else?
And watch. What did I tell you? They love to use 0. So you'll be using these a lot, right there. So help me out. Ready? 3.
No, it's 4.
Oh, thank you. I was reading the wrong one. When this has a prime on it, look. That's a 4. Negative.
Cosine 0.
Everyone help me out with this. Cosine of 0.
1.
Good. Now, hammer, sine of 0. You just look. See it?
Oh, okay, so sine of 0.
Do you see it right there?
Mm-hmm.
The sheen of Charlie Sheen?
Mm-hmm.
0.
0.
I know, if you didn't know them yet, probably after the next few sections, you'll know sine of 0 and cosine 0. Because they come up so often. Plus C. Everyone add a 1 on both sides, let's see.
5.
Well, I'm gonna write it again. Let me write it again, everyone. F prime of theta is negative cos theta plus sine of theta plus a
5.
5. But now we gotta get all the way to what?
F.
F.
F of theta. So that becomes negative cosine theta minus sine theta.
Hey, did I mess up? You're like, yeah, what's the antiderivative of
Negative-
negative cos?
negative
Kayla, I'm just going over here, right?
Negative
Negative
sign.
sine. When I teach Calc 3, I still see this written on tests. People just use it as a guide. Even though you can do it in your head, just like a little safe zone. What's a positive sign become?
Negative.
Is this 0?
No, 5 theta.
Good. Does everyone agree?
Why is it 5?
Do you agree? Think about it. The derivative of 5x was always 5. So what's the antiderivative of 5? 5x. Well, it has theta, so we'll use 5 theta. We're doing that power rule thing, right? When you do this, well, it was a 0. It was 5x to the 0, so it becomes 5x to the 1 over 1. I think the easiest way to see it, though, Amber, is remember this derivative was that? So now you're going that way.
Yes.
The weird thing is a lot of times people accidentally put 0. We're so used to derivatives being 0 of constants, but the antiderivative constant becomes that constant with an x. Well, in this case, it was a theta, all right, because it was all in terms of theta. Now, I still have to put a plus what?
C.
And whenever you've seen this problem, give me another letter.
C1
A.
or K.
K, D, yeah, I love it, you know? Whatever you want, true? You could still use C, but since I already called that C, I might as well make up another constant. Just use like D or something.
Do you
So I'll
have
call
to
you
add,
D.
Do you have to add a constant?
Yes.
Oh, you have to.
Mm-hmm.
Yep, because you did an antiderivative, you have to.
Wouldn't the 5 be the Oh, because then you're going to the.
You got it. You got it. Now, do we have enough information to get D?
Yep.
Uh-huh. F of 0 is, alright, you're 3. Here we go again. What's the negative sign of 0?
0,
Cosine of 0?
1,
0.
5 times 0 is?
0.
If you're wondering, these are where the errors are made.
4.
It's not in the calculus. It's usually in the 0, 1 thing. Student just gets, like a -1 because they thought the cosine of 0 was 0. Cosine of 0 is 1. What do you get for D?
4.
4. So final answer, what is it? Keep you on your test, right? F of theta
Minus cosine theta.
minus theta minus cosine theta plus 5 theta plus
Plus C.
and then I have to put anything else, right?
Never put C.
No, why? We already took care of when we found them.
Oh.
Because it's initial value, does that make
Okay,
sense?
Okay, gotcha.
Yeah, he's got it. So on an initial value problem, you're gonna find your C or your D or your E or you will find those. Unless they only give us that, then we would have to put it. As long as they give us enough initial values, plural. Good deal. Hey, same stuff. The author likes to use S for position, okay? What letter does he like to use for velocity?
V.
V. And what letter does he like to use for acceleration?
A.
So keep in mind, we already know this. Position, velocity, acceleration. Velocity is the rate of change of position with respect to time. Acceleration is the rate of change of velocity with respect to time. This is just like this problem, but are you done copying? What if this was the problem? What if this was A of theta? Then I could have written this as what? V of theta. This would have been what?
S.
V of theta, and then this finally would have became the?
S.
So I just want to point that out, and we'll do a problem like that. I'll pick one from here. Does that make sense? So if you see that, on the test, if I'm like A of t equals this, find S of t, you know, like, oh, A of t is acceleration. I have to go through velocity to get the position. That sound good? All right, try this guy. Can I raise? Good. Hammer, sometimes they don't even write IDP, they don't even say initial value problem, but they will just give you numbers. Okay, they'll just write something down like that. So, all right, here. E of 0 equals 5.
Which number is this one?
This one, I'm doing one like number 61,
Like 61, okay.
okay? So when this one's like 61, but I put 61 for practice, so I didn't want to do exact 61, so it's kind of like we did with that. Remember the one with the straight line? Let's just change it up a little bit. This is like 61, anybody want to know the page? Page 349. So it's like 61 now, V of 0 is 5. S of 0 is 4. And here's what you got. Now, maybe from now on, since it would be like this on the test, we can write this way. Right? Oh, we got it. We got it, Professor Musher. You go this way, right? Oh, we got it. So now, A of t equals, they wrote 2t plus 1. How about t minus 3?
Okay.
Let's try that. Can you, the directions, let me read it to you. A particle is moving with the given data. Find the position of the particle. So you got to find the position. Now what I would write is this. Just to give you a heads up, like you got to fill in this blank. S of t means what? Position. But you got to go from acceleration through what?
Velocity
Velocity. Then go from velocity,
to position.
and you got to get these initial values in those constants, right? All right. Don't do derivative, do antiderivative.
Anti.
T squared.
Is that it?
Over
Over 2, right? I know, we'll always do. You pump it up, then you divide by it, right?
Mhm.
You pump it up by 1, divide by that. Pump it up by 1, divide by it.
Plus C.
minus 3t.
Now what is a 3? Here we go again. Here comes the constant. 3, what letter?
Minus 3T.
Then minus 3t. And then you said plus c. I love it.
Plus C, yeah.
I gotta make sure my t doesn't look like a plus. Here, I'll swing it. Now, do we have information against c? Ah, they gave us something. I need this one. So the 5 goes here. But I love zeros. What's 0 squared?
0.
3 times 0.
How come you don't have C plus 5?
C is 5. Now let's write it again.
Could you explain where you got the 0 from?
Oh, you bet. Now they gave us this, right? Like Farad, they gave me this information here. I love zeros. Well, cosine of 0, you gotta be careful because it's a 1. Sine of 0 is 0, but what's 0 squared? 0. What's 3 times 0? 0, right? I'm substituting the zeros. This is where I put the 0 in for t, and then this is the v of t. So the v of t is that 5, and then the 0 is going in for all those little t's, right? Does that make sense? You gotta love zeros. I'm glad you didn't say like, 2/3 or something. Because then you're like, oh gosh, 2/3 squared? I know. By the way, a lot of initial values are at time equals 0, if t is time. So, I rewrite this. I put my constant back, which was what number?
5.
5.
Now we gotta get s of t. We'll give it a shot, and I'll catch up to you. Because I don't think we've done t squared over 2 yet. Just still do it. That 1 over 2 just stays in front.
So we just did the first part just to find the constant, and now when we have the constant, now we're trying to find B.
Now you're trying to get the s. You got b of t. You're at velocity, now you're trying to get the position.
Oh, okay.
So you're like halfway done the problem.
Yes.
Yeah, you're halfway done. Now, start pumping it up again. Antiderivative. Cubed.
Over 6.
And yeah, look, 2 cubed over 3, right, Saran? But there's a 2 next to it.
So
2 times 3 is just a...
6.
Farad okay there? Yeah, there was a 2 sitting there, just sitting around. Constant stays. 3 times 2 is 6. 3t squared over 2 plus 0 or 5t?
5t.
I
Plus
love it. Be
6.
careful, it's going to happen. You're going to accidentally put a 0 by accident for derivative. Don't these constants always turn to 5t? Now what else do I need? A plus what?
Plus C.
C.
I already use c. You want to use something else?
D.
D. In case
Can't you
someone
just
watches the
put-
video.
Can't you just put in the 5 for C, or D?
C, and that's why. C is 5. I didn't want you to get confused. We found c, which was that. Let's call this another constant, d. But now, how are we going to find d?
You plug in.
Just-
All right, help me out. Where's the 4 go? Where's the 4 go?
In for S.
So that's 4, right? And this is the s of t. Where's these zeros go?
For T.
Right, for out of every t, I'm putting 0. Every t, all right. 4 equals,
0.
I'll go off to the side here. 4 equals 0 cubed over 6 minus 3 times 0 squared over 2 plus 5 times 0 plus d. I like zeros. Just be careful. What's the cosine of 0? It's not 0, it's what?
1.
Be careful with trig functions. That's the only thing you gotta be careful of. And e to a 0. What's e to a 0?
1.
Those are the ones you gotta be careful of. You love zeros, because 0 times 0, 0, 0, right? See them all pop, but be careful with cosine 0 and e to the 0. D is 4, I think this problem is done. Let's fill in the blank. T cubed over 6 minus 3t squared over 2 plus 5t, and then what was d? There you go. Is that okay for the beginning, the test 4, stuff like that? I'll make sure to do one with sines and cosines like the last one too. Yeah. Alright, now we'll go into 5.1. Now what's 5.1 title? When they start showing that symbol and stuff. But I know. Before we just rush into it. Everyone, before we rush into this, Rand, you're very familiar with that. Before I rush into net notation, we got to build on things. So we got to build on this concept of what we're finding. So, we're going to find, at least estimate, area under curves. And we're going to use rectangles. We're going to build rectangles. Now, everyone, it's not going to be perfect, is it? Rectangles have these flat tops, and curves do what? So it's going to be, approximate. Does that sound good? So it may look goofy at first. But I think a lot of you theoretically will think, well, if you do more and more of these rectangles, you can get closer and closer to the actual answer. So we'll start with something very simple. How about y equals x squared? We're all familiar with that, right? Okay. So this is in 5.1. A lot of us are familiar with y equals x squared. And then I'll start throwing down that integral symbol that you talked about, Balraj. We'll put that down to the end. See how that's related. All right, so there's a connection between these antiderivatives and area under curves. There's a connection, right? Now with derivatives, we said that represented the slope of a tangent line to a curve, right?
Mm-hmm.
Well, now you're going to see a connection between this and the area underneath curves. Well, let's see. Let's just start with this guy. Let's just look at a picture of this. Oh, isn't that a parabola? I think I'll just start at 0. And I think I'll go out to 4. Does that sound good? 1, 2, 3, 4. Now at 1, how high does it get?
1.
So when I just go up 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And when I scaled my my y-axis, different from my x-axis, but there's the y values up to 16. Well, 1, it's 1, right? Parabola. What's 2 squared?
4.
4. 1, 2, 3, 4. It's curving. What's 3 squared? And 4 squared?
16.
All right. Well, there's a curve. What we're going to do is we're going to estimate the area under this curve. Now they call this a Riemann sum. I want to make sure the first section where you start mentioning the name. Yep. And when we're going to build rectangles. Now the word rectangle starts with what letter?
R.
R. So when you hear Riemann sum, would you think rectangle? You're drawing what? rectangles. I know this is calculus 1, but when you're in calculus 3, when you hear the word Riemann, would you think what? Rectangle? Now it's going to be three-dimensional, so they'd be rectangular prisms. You built rectangular prisms to estimate the area under some surface that went like this, like some big wave. Like some wave, some surface went like that, but it's still, you can build rectangular prisms or solids underneath it to estimate the volume. Well, here, we're going to estimate the area. Now, what's one way to do it? One way to do it, everyone, is using the left side of rectangles. I'm just going to take like subdivisions in here. Let's say they said use 4 subdivisions. Okay. Now I'm looking at this image, everyone. I can do a subdivision from here to here. That'd be one subdivision. I'll build a rectangle there. I can build a subdivision from here to here. A subdivision from there to there, and a subdivision from there to there. Everyone see the 4 subdivisions we can use? And we'll build how many rectangles? 4 rectangles. Okay? Now I do want to point out this, because a lot of you are good at this. What if they said n equaled 8? Then he wants you to build how many rectangles? 8. So where do you think the width of each rectangle would be? Right now the width obviously is going to be a width of 1. What would be the width of every rectangle?
0.5.
0.5. Very good. You all see that? You'd be like, oh, you got one there, one there, one there, one there. So you follow me? So it does get tedious, but we're not going to get into the ones where you got to like do 1,000 of them. I mean, we'll use technology like Microsoft Excel or something. Just sum them all. But now we're just going to do 4 rectangles. Now, I build rectangles. But when I build this, should I go up here and stop and cut it over? Or should I take this side of this subdivision? We all know what a rectangle looks like, right? Should I go to this side, the right side, and should I build the height? Stop here, hit the curve, cut over like that. No matter what, everyone, I'm always going to stop when I hit the curve. But we got to talk about, are you using the left side of your subdivision or the right side? So they have to tell you that. So our first problem is called a left Riemann sum. All right? Now the author writes it like this, but not every textbook does it. All right? That wouldn't be acceptable. Like, anybody familiar with those AP exams? They couldn't write that because they know that, hey, not every student taking an AP exam would be familiar with L sub 4. But L sub 4 in your textbook represents a Riemann sum. You're going to build how many rectangles?
4.
4 rectangles, then you're going to add up all 4 areas.
Isn't that
And the L is going to stand for which side?
Left.
Left side. All right, but let me write it down. This is called a what? A left Riemann sum. And what are we trying to do? We're trying to estimate the area under the what? Curve.
Curve, yeah.
There's going to be some error though, do you agree? Oh yeah, we're like big time. Well, can we start on this one? So I'm going to start over here. Now which side am I using, the 3 or the 4?
Left, so 3.
Left, so left. So go, and we're going left. Now when am I going to stop? When I hit the curve. So watch. Stop. Stop. Now cut over. Cut over that region. Someone say that?
Isn't there something like L to the something 4 in the calculator or something?
Yep. You don't like that?
Uh-huh.
You can shade it too if you want. Obviously, this thing is going to be grossly underestimated, isn't it? Do y'all have a sense of that? Does everyone agree? Good. Hey, that'll be asked during the test. Like, hey, is this going to be an overestimation or an underestimation? Can you tell? This is going to be a what? Underestimated. We're missing a little. Look at all that we're missing. Okay. Let me keep going. Build this one. Which side?
2.
2.
Yep, I start left. I go up to the curve. When I stop, I'm going to what?
Stop it.
Cut over. Side by side. Do one here. Now you're probably wondering, why did Professor Messenger start with left? Because something weird happens right here.
I can't do anything.
You try to build your rectangle. You said the rule is left side. Okay, go to here. We're going to draw it. We're going to stop when we hit the curve. Watch me do it. Ready? Go. Oh. Do it. I can't, right? What's the height of this rectangle?
0.
0. So that rectangle's area is going to be 0. So sometimes that happens, okay? I don't want to freak you out. Or here, better yet, what if this curve went underneath here? I will still build the rectangle, but I'm going to go down to when I hit the curve. I will. And you go, but won't that give like negative values for the height? It sure will. We'll talk about that. We'll talk about that. You go, what if it goes underneath? Yep. Wouldn't that be negative y values?
Do you do absolute value?
If the question was find the area, but when they say with integrals, we're gonna notice integrals finds net area, so we subtract.
Gotcha.
Yeah. Are you ready? Let's get the area of these rectangles and add them up. Now what's the formula for area of rectangle? Length times what?
Width.
Alright, so it looks like I need an L times W, plus an L times W, plus an L times W, plus a L times W. And this will give me an estimate of the area under the curve.
Mhm.
Now, here, your rectangle 1, rectangle 2, rectangle 3, maybe I should draw them in here. And where's rectangle 1? You don't exist, do you? So what was rectangle's 1's area?
0.
I know. Or I should write it like this. It had a width. The width was 1. But what was the length?
0.
0. Does everyone see that? Now, what's the length and width of part 1?
One.
I mean of Roman numeral 2.
So the length.
How about the width is still just what? 1? But the length is, I'm stuck. How do we get that length? This can happen. How do we get that length?
Oh, so you have to do like x square of 1 and x
I'm
square.
going to have to plug that number into there.
Yeah.
Does everyone agree? Look at this. Hey, what's the width? I can see it's 1. How do I get that length of that rectangle though? You're going to have to look at that number and then substitute it into this equation to get its y value. Does that make sense?
Mhm.
So when this is a width of 1, in fact this width will be 1, this width will be 1, but help me get all these L's here. What's this length? 1 squared, which is 1. What's the next length going to be?
2 square 4.
2 squared. Everyone see that?
4.
So you can write, well, I'll write it as 2 squared so everyone knows where I'm getting these 4s from. And what's this last length?
9. 3 square. Yeah.
Alright, now squiggle. What's the approximate area?
1 plus 4 plus 9. So that's 14.
14. Everyone, if we did inches, we'd say 14 inches squared. Right?
Mm-hmm.
Do you agree? If it was centimeters, okay, 14 centimeters squared. It's not the exact area, but it's what? Approximately the area. Now, everyone, what if I followed this up on the test with this? Part B. Is this an overestimation or underestimation?
And under.
And you see how you really got to kind of draw the picture to find out? Does that make sense? Cool. Oh yeah, hey, sometimes on the final exams, you know what I'd like to do is multiple choice problems? I might just have an image like this. I just have a curve that went like that. And on the other side, I have a curve that go like this. And I say, hey, in which one of these would a left Riemann sum provide an underestimation? Now, how are you going to figure out that answer? You're not going to guess. No, you're not going to guess. You're probably going to draw a little what? Rectangles, right? Now, there's no markings here, but that's okay. You would sit in here and do what? You'd sit here and go, well, let me just think about it. If I did the left Riemann sum, I'd sit here and do what? Left side, left side, left side, left side. Do you follow me?
Mm-hmm.
And you would see which one is the what? Underestimation. See, what would happen if I did left sides on this thing? Well, look what happens. Left side, left side.
Overestimation.
So which one, which one's the underestimation? Does that make sense? I'd like to do that in the final, so I want to make sure you go, oh, I'm just going to build a little rec. If he says left, I'll build from the left side. If he says right, I'll build from the right. I'll see which one is underestimated.
So we can conclude that if the curve is increasing, that's underestimation, and it's decreasing over.
Yes, you got it.
Uh,
It's like your own, I love it. You're coming up with your own theorems now. Like your brain's, like you're thinking about like, well, I guess I can't say theorem hasn't been proven yet, but you got what, some really good what, conjectures going on. Educated guesses, you're going, wait a minute, I bet you if the graph's always
increasing.
concave up and increasing, then a left Riemann sum will be a underestimation.
Yeah.
That is exactly it. If, ready? If the graph is continuous, or if the function's continuous, you know, we can always put that in there. You got it? Hey, now in this same problem, everyone, you see all this junk in here? I'm going to put something down, an integral symbol. I I want to show you what this means, so we get used to this. Integral. Got enough room right here. Let's say this was, I don't know, R of t. Let's say that was the R of t, that function right there. And what was R of t equal to? What equation?
X squared.
R of t
Equal
equal
to
to t squared, right?
T squared, yep.
Someone see that? Well then here, which is x squared, right?
Mm-hmm.
T squared, now what letter did I just use? T? So rather than dx, here I would write
DT.
dt.
I can't say this equals this number, but I could say roughly, right? Now, I want to show you something. You're going, hold up, where's the t cubed over 3 plus c thing, right? That's coming about. We'll talk about that later, the connection. But what I'm saying, this represents, down here at the lower limit, I can say where we started. What was the initial value there? 0. That's t equal to 0. And then at this top, I can put this number. Where did we stop?
4.
4. So listen to this language. That's called a definite integral. The definite integral from t equals 0 to t equals 4 of t squared, right? dt with respect to t, is roughly around 14. But it's not the best estimate because I can tell it's an underestimate. Do you agree?
Mm-hmm.
So on that note, let's do a right Riemann sum. And then again, I want you to do n equal to 4 subdivisions. So how does the author write that? R with a what? 4. But that means what kind of sum? A right Riemann sum. Well, then would you try it? And then I'll be curious, is it going to be an overestimation or an underestimation? Well, it's going to be 4 LWs, do you agree? Okay. True? All right. But I have to draw an entirely new picture. I have to erase this. Sorry. Now, last time I started from the right, I'm going to start from the left this time. I'm doing a right Riemann sum. Which side of the subdivision do I use?
Right.
Why are you starting from there?
I can start on either side.
Professor, just one question. If we do a left Riemann sum from left, could you do overestimate? Can you do that also?
Let's see. Could a left Riemann sum be overestimated? Yeah, I think if it's concave down.
Okay.
Do you agree?
Okay.
If a graph was concave down, do you agree if it was like
Oh yeah,
this?
yeah. Then yeah.
Can you tell?
Uh-huh.
Wait. Left Riemann sum. It would still be
It'd
underestimated.
still be
But it'd
underestimated.
have to be what? The function would have to be what? Decreasing?
Decreasing, yeah.
That's it. That's it. It would just have to be decreasing. Very good. I was thinking concave down, and I start John, I go, wait a minute, no, that's still gonna be an underestimation. All right, everyone. Here I go. I can start from the left to right building these, but I'll just start over here. Which side of this do I use?
Right.
The one. Now watch. Where do I go? Go up to where? The curve. When I hit the curve, I what? Stop, and I cut over that region. So look. Overflow. Look, I'm overflowing that thing. See? Overestimation. Where's the next one? See the image? Go up, stop, cut over. I'm telling you, when it comes to this stuff, if you just take the extra second or two to build this graph, you'll know the answer. Some of you do it, in your head. It doesn't take long to draw this.
So for this one, you're going all the way up to the curve, but the other one you really.
That's
don't.
right, you got it.
So if it's right, you're going all the way
Yep,
up to the
you
curve.
got it.
And the other one.
That's right. All right, what's the width of each one of these? Well, the widths are the same, but I want to help me get these lengths. What are the lengths?
So length is
For the first one,
1,
I plug it, see these numbers are important. I took this one and plugged it where?
1.
Into t squared, right? And when think about this, I could have given you a sine curve, can I? Right? It could have been a sine curve. You would get sine of the number, sine of 1 or something. But I'm plugging 1 into that to get the height. What is it?
1.
The next one is
2 square, 3 square, 4 square.
there's only one thing bad about these problems, they can be a little tedious, right? Especially when they say n equals 16, and you gotta plug in fractions, yeah. Or the worst is when they do trig functions, because then you gotta get out the calculator and get the sine of a half, sine of 1 radian, sine of 1 point, yeah, I know. So when you, keep that in mind when you practice the problems I listed. Kel, when I listed those practice problems, everyone, you're doing those practice problems, the ones where it's like a trig function or e to the x squared, and you're like, oh man, I gotta do e to the 1/2 squared plus e to the 3/2 squared. It can get a little, what's the word? Tedious. You follow me? So expect that. I didn't want you to go, ugh, you know, drive yourself crazy with some of those. You understand the concept, right? Alright, now what's this all come out to be?
30.
16 and 9, 25, 29, 30. Now, who in here has a ballpark idea of what the answer should be roughly? If a right
16.
Riemann sum's 30,
13.
overestimation. Left Riemann sum was 14, underestimation. What would be a good guess? Yeah, you're onto this. Now, everyone, do you agree with this? The more and more and more rectangles we build, the smaller the error. And the idea is send this to how many rectangles? An infinite amount?
4.
Do you follow me? Like, what would really kind of give us an idea of this? You're like, how many rectangles? The mathematicians who came up with these formulas for like these integrals, Repelraj, you're thinking about, they're like, send it to what? An infinite amount of rectangles. You follow me? Cool. Hey, but so far so good? Now, there's one other technique we're going to talk about because this is the most popular. Throughout Calculus 1, Calculus 2, and Calculus 3, what method is used the most often in terms of Riemann sums? The midpoint rule. That means you don't use the left side to build it. You don't use the right side to build it, you use the what? The midpoint. So how about this time everyone, just to save some time, how about I say n equals 2 and I want you to use the midpoint rule. You'll know this, and when you're in Calc 3, you'll be in Calc 3, you'll be like, oh yeah, midpoint rule, I got it. You know, if you understand it, you'll have to do those. I need a whole new picture, huh? Believe it or not, everyone, you're like, I don't feel like, please draw the picture. I think it helps you make sense of it. Now, I'm going from 0 to 4, because this says go from 0 to 4. I'm using the midpoint rule, but I'm using how many subdivisions?
2.
2. Now, how does the author write that? He doesn't use L, he doesn't use R, he uses what?
M.
But not every textbook does it. Most just find it using the midpoint rule, and they have to tell you how many subdivisions though. You do cringe when they say 20 though, because you're like, 20? You get out Microsoft Excel, right? Then, where should the first one go from? There's only going to be 2 of them.
2.
Yeah, from 0 to 2, right? So where's the midpoint? Between 0 and 2.
1.
So when I build this rectangle, do you agree? You're saying this is the width right here. Subdivision 1, right? Subdivision 2. But you're saying use the midpoint of this, would be at the 1. Now watch, I'm going to follow the same rule. At 1, I'm going to build my height. I'm going to build the height of the rectangle. But when I hit the curve, I stop. So watch this. Stop. Now what do you got to do? You notice you got to cut left and cut right? Part of it's going to be what?
Left.
Overestimated. The other part's going to be
Underestimated.
You'll probably understand why midpoint rule is the most popular, because it seems to be most effective in one shot to give you a good balance. Does that make sense? Midpoint rule is the most popular in terms of Riemann sums. Go ahead, Josephine. Oh, okay. Hey, so what would this one look like? What's the midpoint of 2 and 4? 3. Go up, look, stop. Cut left, cut right? Now look what you got. Part of it's. Now let me tell you what I couldn't ask on the final, or on your test. And I'll get your question, Josephine. I couldn't ask this. Is that an overestimation or underestimation? Because you'd be sitting there trying to what? I can't tell. I don't know if this was what? More than that, right? Is that area more than, right?
Hard, yeah.
It'd be hard to tell. Does that make sense? Now, have mathematicians come up with theorems about graphs that are concave up?
Mhm.
And whether a midpoint rule gives they have. They've explored this. They wanted to know, does midpoint rule for concave up curves increasing or decreasing actually give an overestimation or underestimation? But we don't have to worry about that at this point. Go ahead, Josephine.
Is that how you apply the n to figure out how to do the rectangles?
How do you apply the, what was
The
that?
n, like you know the n equals 2.
Oh, so this means how many rectangles you'll build, and they will give that to you. That means how many subdivisions you're gonna use. So when there's two, you and I are looking at this image and go, okay, that means I need to use 2 of these, right? Cool. Now, I have a question for you, Josephine. Do you want a math formula? So you can figure out how many you're always gonna use every time?
Well, I'm more concerned with like how do you figure out where to put your rectangles?
Oh,
You know you're gonna have 2. I mean like
So,
that would be a simple example.
they have to be, it was from 0 to 4, right?
Yeah.
And so we had to use 2 of them, right?
So you just figure out the
Well, what did you think? Were we gonna build one like right there and then one like that? That would be kinda weird, wouldn't it? If you gotta build 2 rectangles in here. You gotta go from 0 to what? 4. So should I build one here and then one like that? And then the other one's like this? What would be your logical idea?
just right in the middle.
Yeah, right in the middle. Does that make sense?
So does the midpoint rule always use n equals 2?
No, depends on the, how many.
Depends. But I think you want a formula for this, so I'm gonna give it for you. Ready? So if you take this b minus a, what was it? What if you subtracted these right here? And you divide it by this number, it'll tell you how many rectangles you gotta make.
What is D and what is A?
If I call this upper value b
Oh, B, okay.
and this lower value a,
Uh-huh.
I can make a formula for you, Josephine, so it's easier for you. That's A, that's B. And B minus A would be what? 4 minus 0? Now, how many did they have right here? They said N equal what? 2? And this will tell me how many you're gonna have to, what's gonna be the width of each subdivision. That will be, ready? Call that change in x. In this case, though, Josephine, for your notes, did I use the letter t here? I never wrote it here, but I changed it to a t squared, where the function was r equal to t squared. So that would be your change in t. That way you'll never be confused. So watch this. Let's say you went from 0 to 16, right? You had a graph from 0 to 16, it went like this. Cool? So B would be 16, A would be 0, and then I said, you need 4 subdivisions. Could you tell me what the change in the t would be every time? So if it would be 4 subdivisions, it'd be 16 minus 0 over 4. So what is that number?
4.
So every 4 tick marks, you would build a rectangle. There you go. Cool. But was everyone in here be able to do it like logically? Just to go, oh, I gotta go from 0 to 4, I need 2, I just cut it what? Right down the middle? Is that what I cut that?
Isn't delta t dt, right?
That's right.
Oh,
That's meaning the change in the t values. But that's a formula, right? Wouldn't that work every time? So, but if you want a formula to say, I want to know how far I'm going to have to go change in this direction to build my what? Rectangle? This could always work. Does that make sense? Cool. Hey, now what do we get for our first rectangle? What's the width?
1.
Oh wait, look at our image, everyone. If I call this part the width. 2. What's
Oh,
the
yeah,
length?
with 1.
Gotta plug that number in, right? 1 squared plus, what's the width?
2.
And look over here, the width is still, is it 4 or 2?
2.
See that? How wide is that? That's a width of 2. Now, is there a math formula for every one of these widths? That's it, if you ever want to use it. right? I mean, if you wanted a real formula, always figure out would be the width every time. The change in the x will be your change in t will be your width. So make a note of that, Josephine. You go, I can always use that formula to find my width every time. Because you can do width this direction, change in t, change in x. But to get this, I gotta plug it where?
At 3.
Into
9.
the original,
So
which
9.
is, so what's this number, Owen?
19, 20.
Yep, because 3 squared 9 times 2 is 18 plus 2 is 20. Which one of the three is probably closest to the real answer? The midpoint rule, why?
Cause it's between.
It's got like a
it's
bounce.
Between 30 and 14.
You got, that's one way. And look at the image, like, lost some, but I gained some. I lost some, but I what? Gained some. The more you do that would be more. But see, a lot of you have a good idea. You go, yeah, but why don't you take these, add them together, and divide by 2, right? She's gonna do it.
That's 22.
Oh.
Is that right? Now, anybody curious
Add
what the
them.
exact answer is? You must be. Can we
Yeah,
talk about that?
22.
Come on, you must be curious. What's the exact answer? You can find it through calculus. And you go, what do you do? Ready? Maybe I shouldn't do this because the author waits a whole nother section to show this, but why not? I'm sure you're all curious, right? Some are laughing, like, yeah, I know, we can do it now. Let's find the exact answer. I go like this. What were the numbers? 0 to what?
4.
What was the function I was using?
T squared dt.
T squared dt. Now, we spent the whole hour doing antiderivatives, right? Right, everyone? All that time doing antiderivatives. What's the antiderivative of t squared?
T cubed divided by 3.
Now, don't forget something. You got to put your what?
C.
Plus c. Now, we'll talk about that, plus c. Because you go, wait, aren't we supposed to get definite answers? Watch what happens. So when there are numbers there, these are definite answers, right? Something cool's going to happen. But I'm going to put my plus c for now, because this is the first time you and I are doing this. This symbol is gone. And when it's gone, it's gone. We found the antiderivative. So what I want you to do is go off to the right here and put a vertical line. At the top of your vertical line, if you want to put little hooks on it, you can. Some mathematicians do. At the top, put that same top number. What is it?
4.
4. And at the bottom, put this number.
0.
Now, what do you think we'll do with these numbers?
We're gonna plug them.
We're going to plug them in for what letter?
C.
C.
Oh, not for C.
T.
For T, right?
To
Because
find
really, I didn't write it. That's T equal to 0. That's T equal to 4.
4, yeah.
That's T equal to 4. That's T equal to 0. Now, I'm going to plug them in here, but I want you to understand, this is like accumulating area. So when you do this, we're going to subtract the two values we get. So we'll plug in a 4, get the number, then we'll subtract the value you get when you plug in a 0. But this will give us what kind of answer? Oh, not approximate, but what? Equals exact. And it's probably going to be around, Amber, what was your number again? What was between this? 22. So it's probably around 22-ish, 20-ish, right? Let's see what we get. So I'm going to plug a 4 in here. What's 4 cubed over 3?
21.3.
Oh, yes, 64 thirds. Y'all agree? 4 cubed is 64. Now I have to put plus what?
C.
See? That was from plugging the 4 in.
You have to. Okay.
That was from plugging a 4. Now, do you remember I said put a subtraction sign?
Oh.
Or I'll put a minus sign. Now what number do I have to plug in?
0. 0.
Plug in 0. What, for what letter?
T.
What's 1 cubed over 3?
Not 1. 0 cube.
I mean 0 cubed over 3?
0.
0 plus C.
And my favorite part, I hope it's your favorite part, what happens to those C's?
It cancels out.
So everyone, ladies and gentlemen, guess what happens whenever you do, this is called a definite integral? Guess what happens every time you do a definite integral, what happens to the C's?
I can't swallow.
So a lot of you aren't even going to write the plus C when you do definite integrals because they're going to what anyway?
Cancel out.
Cancel out. Does that make sense?
So it's just 64 divided by 3. And
So what's 64 of a third about?
21.33.
That's exact. So what's the exact area?
21.3.
Now, can we have fun and do this on our calculator? Can we all do this on our calculator? You got yours? Everyone got it? Would you go to y equals? Josephine, you got yours? Let's have fun. Go to y equals. What's the curve again? X what?
X squared.
X squared? All right, hit graph. Oh, wait, you do it. Y equals x squared, hit graph. If your windows out of whack, zoom 6, right? Unless you want to go from 0 to 4, but no, 0 to 10, that's okay, it's a nice window. Go to second calc, which is that trace button. Second trace. Which one has that integral symbol? Which one? Go to 7. What's the first question?
Lower
Lower
limit.
limit.
What's the lower limit?
0.
0,
It's 0, and then what's the upper limit?
4.
4,
And what will it do? It should go, oh, cool. Isn't that cool? Don't forget about this. This is a little cool button. Did it work? 21.3, and there's probably a 4 at the end. Or it gets that. Remember, we sometimes get the round off error at the end.
Yeah, I don't get it.
It didn't work.
Hold on.
What?
Do this, and then do lower limit.
Oh no, just pick the number. Let's start over. There it is. Grab. Set trace. When you hit this number 7, let me just go. Boosh. Hit enter. Upper one. What's the upper one?
4.
Boosh. Hit enter.
Uh,
That cool? Yeah, we don't need that darn trace thing anymore. Just put those numbers in. Hey, isn't that awesome now? So, what's the exact area?
21.3.
So, I mean, maybe we could write out a calculus formula for this. What is this really equal to? Riemann sums. How many rectangles would you have to build?
2. Oh,
I mean,
No.
really, theoretically. I did too, but theoretically, if you keep squeezing them, squeeze these tiny, thin rectangles, there's going to be less, what? Area. So, how many?
Infinite.
Infinite amount. What's the width going to approach?
0, almost 0.
You're onto it. What's the width of the rectangle going to approach? You're onto it. So we use, you go, what word do we have to use in calculus to say that?
Limit.
So how about this? You want to see the goofy math notation? What would it be? You say, okay, the limit. And if you want to know what page I'm copying this from, you'll see this on page like 374, right? The limit as n approaches, how many of them? How many rectangles? Oh, there you go. Okay. This is just math notation. We're on to this. And you go, okay, summation. That means, by the way, anybody familiar with that? That's the Greek letter sigma, it means summation. Cool? I know, it's the Greek letter sigma, it means summation. They use the letter I, don't let that bug you, they just decide to use I for index, you know, and I equals 1. They said go to n because you're setting this thing to an infinite amount. Now, and what's the area of rectangle?
Length times width.
Length times width. But regarding a function f of x,
Oh, x.
how about I call length f of x, and then the width just change in what? Change in x. Does that make sense? So here comes my length times width. Ready? Length f of x. Width.
Change.
Change in x. Now, the author put a subscript I here because he's trying to tell you you're going to sum an infinite amount of these. Like x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, x sub 8, like x sub a million, x sub a trillion, you know what I mean? And this turns into, let me put an equal sign, ready? Da-da-da, da-da-da, da-da-da. Isn't that cool? Now you have to go from some what? Some certain value to what? Does that make sense? Now we have, here's the, everyone, you want to write the rest of the wording from this? If S is integral on interval A to B, you gotta make sure there's no what? Holes in your function, right?
Continuous, okay.
Yeah, a continuous function. There it is. That sound good? Oh, again, Amber, if you like this, what would change in X represent? What would change in X represent? B minus A over this what? This N. I'm using an infinite amount. Cool. Hey, last problem. Let's do application. Sound good? I think you'll love this on a test. I'm going to have you do something, you know, real life data. Not some goofy thing like this, but real life data. So I'm going to 5.1. Let me look for something good. Come on. You got a, all right, they got a motorcycle. They got a runner. That's it. And when they gave the speed of a runner a number 13, they gave a motorcycle a 14. All right. And when can I take number 14 and reword it in some way and see how you do with it?
Okay.
Oh, here you go. Can I erase this? You sure? Hey Josephine, I liked your question earlier, like, is there a way, this will always tell you how many you make for each, and that's your width every time. By the way, same thing in Calc 2, and as you go into Calc 3. You can remember that. B minus A over N. The only thing is Josephine, in Calc 2 you may have two of these. So you do a B minus A for that one, and a B minus A for that one. That's the only difference. I think you all will like Calc. All right, here we go. Here's the table. They give you velocities. 0, 12, 24, 36, 48, 60, 30, 28, 25, 22.
24, 27.
Now I want to make sure I can ask this question on the test. Did you notice it went back, kept going back up? So I would do this on my test. I'm going to change these numbers if you don't mind. I want them to change the actual velocity of this motorcycle. 10, 5. The only reason I wanted to do that, Art or anybody, if you're curious, is because I want to ask a question about the overestimation or the what? Underestimation, okay? If those original numbers are there, you've been, hey, I don't think there's enough information here. Does that make sense? I want to make sure you can see, oh, this graph kept going, so you can see if you got over or under. So, letter A. And I want you to use a left Riemann sum with 5 subdivisions. And then I would say this, just so there's nothing ambiguous about this, with equal length. The subdivisions have equal length. Okay? And I want you to use a left Riemann sum with 5 subdivisions of equal length to estimate, here we go. Ta-da-da. Ta-da-da. This thing, it may be bothering you right now, then that just means I'm using the letter T with respect to T, okay. Be a T, and I want you to go from T equals 0 to T equals 60. Now would you try it? Now I'll be honest, it never said you had to make a drawing, but a lot of you will probably on my test make a what?
Correct.
Probably draw it.
Did I say 60?
Yep. Sorry, yeah, that 0 looked a little goofy. Hey, when you do this, and I asked a couple questions to follow this. When you do this, I think a lot of you will make a drawing. Because on left, right, where's the curve, right? So what would you do? Oh, you just go over here to the side, right? Just go like this. Doesn't have to be perfect. Go like this, go like this. This is T, this is what?
V.
B T. Now what did the T's go by? What were the increments? 12, 24, 36, 48, and 60? I actually love seeing these, but it doesn't mean you had to. It never said draw a picture, right? I think it helps. Well, let's estimate these. How high was this?
30, that is 0.
So that was at 30, and then how high was this?
28.
I like to label them, 28, it's got the 25. Look, I'm just estimating, can you tell? Claire, I'm like, that's about 25 in height. I see it's going down, what's this?
24.
22, 10, and what? 5. Does everyone see? I was just estimating the heights there, right? It doesn't have to be perfect. And then I connect it with my pencil. It looks kind of, look. It's just a little curve. Not perfect though, but I think drawing these helps. Because you know what's coming up. is your final answer an overestimation or an underestimation? Of 0 to 60, B of T. Now you see the importance of Riemann sums. Sometimes in real life, this is all you have.
Professor, are you going to say, is this an overestimation or underestimation from left side or right side? Do you have to mention that or that?
I would say, I would follow this question up after I did a left.
Oh, left, okay.
And I should, when I write this, I should be more clear, but I'll be indicating that last answer.
Okay.
So just remember, when I say is this, I'm talking about your last answer, where we did a left.
Does the formula you said B minus A over N work?
And that will give you the width of each what? Rectangle. That will give you each width. So try it. What's B minus A?
12.
B minus A is 60 minus 0 is 60, but what was N? 5. So let's try that. Josephine, we're going to try that formula to find out, well, what's going to be the width of each one of these. B was 60, A was 0, 60 minus 0 is 60, 60 divided by 5 gives us what number?
12.
12. So that means every 12 I'm going to build a rectangle. Does that make sense? You got it. I can go off to the side. What was that again? Change in this what? X. Well, in this case, what's the letter?
T.
So that means for every 12 I build a what? Rectangle.
Rectangle.
Now I have a question. Belraj, that works every time. Josephine, that works. Raise your hand though if you just kind of do this logically. I bet a lot of you just, like you, I think I follow you. That's totally fine. You just go, okay, I need 5. You're like, 1, 2, 3, 4, 5. That's totally fine. I get a lot of students that just, they don't have to do this math here because they can see in their eye, if I need 5 of these, they're equal length, then I'd have 1, 2, 3, 4, 5. 5 rectangles, 5 subdivisions. But yes, always works. Every time, Belraj. Every time. So now, which side am I building this with?
From the left, right? So from 0.
All right, here we go. Why is this important? Because then when I do my LW plus my LW plus my LW, I'm telling you, I get more errors on this problem than the complicated calc problems. Because people try to do it with no picture. They just go, oh, it's just those numbers in the table. But you got to be careful. Which length am I using from that first number? Can you see it? Like the width is what? 12.
12.
What's that length?
30.
30. All right, so here we go. What's the next one? Maybe I should draw it. Can you see it?
Mm-hmm.
Do you see that, Amber? How I'm really thinking like left side, stop, cut over, right side. So this length is 28, isn't it?
Mm-hmm.
What's the width though? Not 24.
12.
I see this on tests all the time too. Look at it. That's not right. What's the width of that rectangle? It's that number, Belraj, you told me. You said that change in X is 12. You always use 12 for your width. That's the width. Now you see a pattern to this?
Mm-hmm.
30, 28. 28, what's the next one? But sometimes students go too far and they go to the 5. Don't go to the 5, it's just gonna go to what? Trust me, I know there's people in this class, you get really fast at these. I think that's awesome. I just always say what? Be careful, right? Be careful. Is this what's gonna happen? Because look at the last one. Just take the time to draw these.
That's an overestimate.
Everyone, did I ever use this 5? But if I used a right Riemann sum, I would have. Do you agree?
Mm-hmm.
Now think about it. If I did a right Riemann sum, I would have used a 5, but I wouldn't have used the...
30.
You got it. You got it. That's what I mean. If you start doing it, people do this without even drawing pictures on tests. Just be careful. Now, I don't know what this is. Did anybody try it?
1380.
Oh, thank you. 1380, huh? Now, letter B, over or under?
Over.
But be careful on the here, I'm just gonna circle. Be careful on the test, I might have the data go like this. What do you think it would be if I did a left 3 months on? Yeah, I could, but what I couldn't do is I couldn't make it go up then down. It wouldn't be enough. And then letter C. That's a good note to end on, ready? This was velocity. The units, everyone, for this problem were in seconds. So I gotta point this out. Time was in seconds. Velocity
Feet per second.
was in feet per second. This was a motorcycle. Letter C, I'll write this out if anyone wants a copy, you've got a minute. And when using correct units, make sure you use correct units. Explain the meaning of your answer in letter A, the meaning. And I think a lot of you will get it. What does that number mean in terms of this real life problem? What does it find? Letter A.
So position.
All right, everyone, those are velocities, huh? And we summed all this. But we're doing what? Antiderivatives. And today we went from acceleration to velocity. And when we did the antiderivative of velocity, we get back to what? Position. So in terms of real life application, what is this 1380 representing? Not the position of it, but the total what of that motorcycle? The total
Feet per second.
distance.
Feet. Yeah.
The total distance that that motorcycle traveled over how long?
60 seconds.
So take some time to write this right before you leave. You'd say this represents the total distance that the motorcycle traveled over the 60-second period. But don't say, hey Amber, don't say feet per second because it's distance. It would just be in what units?
Feet.
So you would say, how many feet would this be? The bike roughly traveled how many feet? Like, put that in words. This motorcycle traveled roughly 1380 feet over the 60 seconds. Does that make sense? So, hey, I'm going to be careful right before we leave. What if I did like flow of oil out of a tank? And we did the same thing.
So
So I
liquid.
give you all the rates of the oil. It was flowing at like 32 gallons every hour. And then in the end, I get the letter C, and I go, what does this mean? What would it represent, that final number after the interval? The total amount of what?
Gallon.
Oil that leaked out of the tank. Does that make sense? You integrate a rate, you get the total amount. You don't want to follow that?
Mm-hmm.
So if you want to put an analogy before you leave, like rate of oil flowing out of a tank, you get the total amount of oil. Rate of water coming out of a tank, you get the total amount of water, right? Like someone's draining a swimming pool, and they get the rates of all the rates. You get the total amount of water that came out of the swimming pool.
Antiderivative is easier than derivative.
Really? Hey everyone,
At least what
no
I've seen.
class what?
Tomorrow.
Tomorrow. Someone got that?
I will
Hey, Raj, could you tell Farad and
Yeah, sure.